Hi, everyone. Let's first talk about domain and range for sine and cosine, the basic sine and cosine functions. All right, y equals sine of theta. All right, let's take a look. Domain. What are the x coordinates we pick up? We pick up all real numbers as x coordinates. Domain is all real numbers. What about the range? The y coordinates we pick up? Only the real numbers between -1 and 1. Even if we zoom out, we're just wobbling between -1 and +1. All right. Same for y equals cosine of theta. That's just a horizontal translation of the sine graph. Same domain, all reals, same range, still from -1 to 1. So if f of theta is sine of theta or cosine of theta, the domain of f is all reals. We never have a problem. The range of f is the closed interval from -1 to 1, which makes sense because we're talking about sine values and cosine values. We're talking about, on the unit circle, the possible y coordinates and x coordinates we get along the unit circle as we travel all around the unit circle. Okay, so we pick up all the real numbers between -1 and 1 for both y, or sine of theta, and x, or cosine of theta. All angles work out. We never, sine and cosine never have a problem for any angle. Domain is all reals. All right. Now what happens if we put a number in front of sine of theta or cosine of theta? In general, how do you graph f of theta or y equals a sine of theta or a cosine of theta? What could happen? Let's ask Desmos. Here's y equals sine of theta. What is the graph of y equals 2 sine of theta? Remember chapter 1. What happens if you multiply the right side by 2? Y equals twice sine of theta. You double all the y coordinates. That leads to a vertical stretch. From the green graph to the black graph, it's a vertical stretch by a factor of 2. What about y equals 3 sine of theta? That's the red graph. We're stretching by a factor of 3, and so forth. So if you're multiplying sine of theta by a number greater than 1, you're getting a vertical stretch. But let's say we multiply by 1/2. What happens if we multiply by 1/2? Y equals 1/2, or 0.5 times sine of theta. We're going from the green graph to the blue graph. That's a vertical shrink. We're squeezing the graph towards the x-axis, or the theta axis in this case. Y equals 1/3 of sine of theta. It's like almost gravity almost. That dark green, thick green graph, that's very squeezed towards the theta axis. What if a is negative? How do you graph y equals the opposite of sine of theta? What happens when you multiply the right side by -1? Remember section 1.4. Y equals the opposite of sine of theta. That's the purple graph, upside down. Again, the green graph here becomes the purple graph over there. The graph is flipped. It's reflected about the theta axis, which was the x-axis. Reflection about the horizontal axis. Y equals -2 sine of theta. Two things happen. Okay, as we go from the green graph to the black graph, we get a flip, a reflection, and also a stretch. So what can A do? A can lead to a vertical stretch or shrink, and if A is negative, it leads to a flip, a reflection about the horizontal axis. Again, if A is positive, and if A is greater than 1, it's a vertical stretch. If A is like 1/2, strictly between 0 and 1, it's a vertical squeeze. If A is negative, you reflect about the x or theta axis. Okay. Now, with our general frame method, here's the deal. We're going to ask if we have a sine function or a cosine function, and we're going to ask if A is positive or negative. If a is 0, you're destroying it, right? That's not a trig function. All right, so if a is positive, we have our classic shapes, our classic cycle shapes. A good morning graph for sine, a valley or a curvy V for cosine. And then if a is negative, we flip or reflect about the horizontal axis, this middle line. So instead of good morning, we have good evening for sine. Instead of a valley, we have a hill, kind of a pimple up there for cosine. We flip, we turn it upside down. These are the cycle shapes. So if we're going to graph one cycle for a transformed sine or cosine function of the type I could give you, then you're either going to graph a good morning shape, a good evening shape, a valley shape, or a hill shape. Now, granted, consider the graph of y equals sine of theta. It's true that all 4 of these shapes are achieved and attained eventually on that curve, but we're going to describe a method where you're going to use one of these 4 particular shapes in order to graph one cycle using our frame method with appropriate coordinates. So remember these 4 shapes. Okay. A determines the amplitude for the function or the graph. So if we graph y equals a sine of x or y equals a cosine of x, I'm going back to x now, all right? The absolute value of a is the amplitude of the graph. It's half the height of the graph. So for example, here's the graph of y equals cosine of x. The amplitude is 1 because the coefficient, well, it's kind of a coefficient. A equals 1. A equals 1 here. Okay, the total height of the graph, the total height of the graph is 2. Half the height of the graph is 1, and that's the amplitude for the function or the graph. The range is going from -1 to 1. What about y equals 2 cosine of x? Okay, so here's y equals cosine of x first in green. Here's y equals 2 cosine of x. What happens? Vertical stretch. We go from the green graph to the red graph. What happens? The amplitude is doubled. The amplitude goes from 1 to 2, and the range, by the way, is now -2 to 2. It's also stretched by a factor of 2. All right. So for y equals 2 cosine of x, the amplitude is 2, half the height of the graph. The total height is 4, half the height, the amplitude, is 2. Y equals 1/2 cosine of x, that's a vertical squeeze. The amplitude is 1/2, it's smaller. For y equals -2 cosine of x, we're taking this v guy and turning him upside down, all right? Well, this guy's upside down, but these 2 equations here, y equals 2 cosine of x and y equals -2 cosine of x, the amplitude is the same. It's 2 in both cases. The absolute value of -2 is +2. Amplitude, by definition, is always positive, okay? Amplitude is the absolute value of a, and it's half the height of the graph, half the height of the graph. So we've described the impact of a, this number in front of sine of x or cosine of x. It can lead to a vertical stretching or shrinking, and if a is negative, it leads to a flip. Next, we're going to consider what happens if we put a number in front of the x. That's next time.